Okay, so we have derived these two equations. Okay, so forward error, ith order forward error is nothing but the previous one minus previous backward error multiplied by the ki. Okay, so these two equations we have derived. Now, if I have not predict anything, what is E0m? What is E0m? E0m means that what is error? Error is that sample value minus estimated value. So, if order is 0, that means I am not estimating anything. So, error is nothing but a SM. So, similarly backward error is also is nothing but a SM. So, I can say E0m is equal to B0m is equal to SM. Okay. Now, try to draw the signal flow diagram, or I try to draw the lattice filter structures using these three equations. So, this is the equation number 3. So, what I said, if I know SM, I know SM. So, which give me the E0m, okay, and B0m. Now, I want to find out the E1m. I want to find out E1m. So, what is E1m? From this equation, if I say E1m is nothing but a E0m minus ki k1 into B0m minus 1. So, what is B0? This is B0m. So, if it is B0m, I want to produce B0m minus 1. So, I can say z to the power minus 1. Okay. So, SM is feeded here, speech signal is feeded here. So, E0m, B0m is equal to SM. Okay. Z to the power minus 1 delay, if I applied, I get B0m minus 1. Okay. Now, if E01 is nothing but a E0m minus ki into k1 into B0m minus 1. Similarly, suppose I want to predict B1m. So, B1m backward prediction error, B1m again I put the I equal to 1 in here. So, I can say B0m minus 1 minus k1 E0m. So, I can say this one is nothing but a, this is E0m, this will be minus k1. So, if I say that I want to predict E2m and I want to predict B2m. So, again I have to delay z to the power minus 1, and I can say this signal should be added here with minus k1, and this signal should be added here to get the BTN minus k1. So, if you see, the same structure is repeated here. So, this is called lattice structure, single lattice, second lattice, third lattice, and that way I can get the value of EPM. If the pth order prediction, so I get EPM, and from here I get BPM. Okay. So, that is called lattice structures. So, what is EPM? EPM is nothing but a error. So, if I say I want to implement APZ, this is the implementation of APZ. Implementation of APZ. Why? If you remember in my first class, what I am saying, that if the whole speech production system is linearly modeled, LTI systems, or it is linearly modeled, then I can say if I apply, if this is my Hz is my vocal tract transfer function, Hz in here. So, what I said, if we apply impulse AUGZ, glottal impulse with amplitude, then I get speech signal which is SZ, or I can say in time domain I can write AUGN, this is HM, and I get SN. Okay, what is HZ? HZ is nothing but a gain, either A or write G, gain A or G. I can write the gain as a G also. So, I write the gain as a G. So, G by 1 minus k equal to 1 to P alpha k z to the power minus k. So, this is nothing but a prediction error, which is AZ. So, I can say H is equal to G by AZ. G is a constant. So, I can replace that HZ by 1 by AZ, or I can say if I apply AZ, if I implement AZ and apply SZ, I can get error EZ, which is nothing but a, I can get EZ or forward prediction error or backward prediction error. At the PS stage both will be same, okay, EZ. Or I can say if I apply SM, time domain signal, and if I implement this AZ, I will get EJ, EM, EPM, or which is nothing but a G into UGM. So, from output speech, speech is nothing but a excitation into the transfer function. So, this is AZ. So, if I subtract this one, only remaining is the glottal excitation. So, that is gain into glottal excitation. So, error function is nothing but a gain into glottal excitation. So, suppose for a given speech signal, find out the prediction error or prediction error signal, which is nothing but a gain into glottal excitation signal. So, I can apply the speech signal and implement AZ. I can implement easily AZ if I know K1, value of K1, K2, in second stage it will be K2, so third stage it will be Kp. So, if I know the value of K1, K2, Kp, and if I implement this diagram, this thing in the digital computer, and then if I apply speech signal, I get the excitation signal. I get the excitation signal. Okay. So, this is called prediction lattice filter for AZ or error filter implementation. Lattice filter for AZ or error filter implementation. Now, suppose in speech synthesis, so I told you one thing. Suppose I have a speech signal which has 8 kilohertz sampling frequency, okay, 8 kilohertz sampling frequency sampled signal, and I take a window of 20 millisecond and it is encoded at 8 bit, 8 kilohertz 8 bit. So, in 20 millisecond how many samples will be there? 160 samples will be there. Now, each sample is 1 byte. So, I can say this 20 millisecond window can be stored or can be required 160 byte memory to store. Now, suppose the problem is that I want to transmit this 20 millisecond speech from this point to this point. So, my bit rate is 160 byte I have to transmit it. I have to transmit it 160 byte from this point to this point. Can I reduce it using this LPC method? So, instead of transmitting 20 millisecond, so since it is 8 kilohertz, what should be the order of the prediction? So, for Fs is equal to 8 kilohertz. So, I can say Fs by 1000 plus 2 for radiation and 2 for glottist. So, I can say it is nothing but 8 plus 2 plus 2, the 12th order prediction is required. 12 to 14 order prediction is required. What is the meaning is that? That means that I require alpha 1 to alpha 12. Okay. So, if it is alpha 1 to alpha 12 and each one of the alpha is encoded with let's encoded with 4 byte. Let's take 4 byte. So 4 into 12, 48 byte. I require to encoded the alpha value. Now it is said that if I know the alpha value or k value, ki value, let's ki value. So if I know the ki value, then at the receiving side I can say that I can implement the filter which is 1 by Az, and I can implement 1 by Az, and if I apply the gain and error signal, what is error signal? Nothing but excitation. So excitation, if it is voiced, then it is excitation is nothing but impulse. If it is unvoiced, excitation nothing but a noise. So what information extra things I require? Whether this segment is voiced or unvoiced, that required 1 bit. If it is 1, then it is voiced. If it is 0, then it is unvoiced. Okay. If it is voiced, then I have to generate the impulse. Who supply the impulse period? That is also transmitted. So I can say again the value of F0 will be also transmitted. So if F0 value is transmitted using 1 byte, let's F0 value and this voice unvoiced information is transmitted using 1 byte. So 48 byte plus 1 byte plus 49 byte is required. So if I transmit instead of 160 byte, I can transmit 49 byte and recover the signal same segment at the receiver end. This is called Lpc encoding. So in Lpc encoding, I only transmit this alpha value, whether it is a voiced or unvoiced or F0 value, and then receiver side I connect. So I can say if I want to draw the decoder, so I can say if it is voiced, this is a impulse generator, then there is a gain, gain also transmitted G is 1 byte. So gain is transmitted using 1 byte, so it is 50 byte. Okay. So this is gain, it is multiplied with gain, this is gain, this is noise source. There is a switch, if it is voiced, the switch will be connected to here, if it is unvoiced, it will be connected to here, and then I implement 1 by Az, which is supplied from Ki value. Then I get the speech signal back. So how do you implement Az? I know how to implement Az. Now I know that if it is Az and Hz is nothing but a G by Az. So I want to implement 1 by Az. I have to implement 1 by Az. How do I implement 1 by Az? Az implementation is already explained. So I have to implement 1 by Az, which is nothing but a Hz. This is required. This is called lattice formation of vocal text transfer function, which if I implement that using Ki value, from this information I can generate the speech signal. So how do I implement 1 by Az filter? Okay. Let us try to implement 1 by Az. Az I can implement from that equation. So 1 by Az. Okay. So what I want? I want to supply error signal. EPM I know. Okay. Inverse. I want to inverse it. So that why I have applied SM and I get EPM. Now I said I want to apply EPM and reverse the signal and get SM back, that is 1 by Az. Okay. So at the output what I said EPM is the error signal. So I know EPM, let us EPM I know is the error signal I know. So if you remember the equation, EIM is nothing but a EI minus 1M minus Ki into bi minus 1 m minus 1. So, if I know EPM, what I have to estimate? I have to estimate EP minus 1 m. Okay. So, if I say EI minus 1 m is equal to EIM plus KI into BI minus 1 m minus 1. So, I can say EP minus, so instead of I put P, EP minus 1 m is equal to EPM, which I know, plus I have to know, I have to know B P minus 1 m, m minus 1, B P minus 1 m minus 1. Okay or not? So, if I say this point is my BPM. So, I have to apply a z to the power this way, this is coming in this way, I can apply z to the power minus 1 to get P m minus 1. Okay or not? So, if it is that BP minus P minus, so if it is B, this one is BP minus 1 m, this one is BP minus 1, this is BP minus 1 m minus 1. So, I can say AIM BP minus 1 m has to be added here with multiplication factor Ki K1, which is K1 is Kp, I is equal to P. So, I can say EP minus 1 m is equal to EPM plus Kp into BP minus 1 m minus 1. Okay. So, if it is BP minus 1 m minus 1, I can get it. Okay. Now, what is BPM? BPM is nothing but a BPM is nothing but a, what is BPM? BP, I can say BI, BIM is nothing but a BI minus 1 m minus 1 plus minus K1 Ki E I minus 1 m. Now, I can say BPM is equal to BP minus 1 m minus 1 minus Kp E P minus 1 m. So, I can say if this is my this is my BPM, this is my BPM. So, if it is my BPM, this is my BPM, this point is my BPM. So, BPM is nothing but a BP minus 1 m minus 1 is okay, minus Ki into, so this has to be, so this is here, okay. So, this I can say this has to be again come EPM. So, it is what is BPM? EP minus 1 m, EP minus 1 m has to be come again in here to and multiply by minus Kp, get the BPM. Okay. So, if I say I just want to draw the drawing very neatly, then I can say this is my figure. So, I can this one and I can say this is this one. Okay. This direction multiplying factor and this direction multiplying factor. Okay. Similarly, I can calculate Pi minus 2, I can calculate Bi minus 2 and draw the figure. So, you can draw the figure in home, you see the slides is there. So, you can see the slides also if you want help. Ultimately, if you see, once I go to the 0, what is E0 m? So, you can say E0 m is nothing but a E1 m plus K1 into B0 m minus 1. Okay. Now, E0 m is nothing but a my Sm. E0 m is equal to Sm. So, this is the picture. E0 m is equal to B0 m, and if I want to calculate B1 m, B0 m, I require B0 m minus 1, B1 m minus 1. Okay. So, I can do that. Okay. So, this is the implementation of Hz. So, details you can see these slides and you draw this. Now, try to implement in a program also. I can implement this in a program also. So, if you see the algorithm is given. You can go through this algorithm and implement this in a program. So, I give you a task. What is the task? Let us record in your own voice, record the vowel A. You record vowel A. How you record? Let us for some time you say A. Okay. Then you take the signal of 20 millisecond from the, so there is a signal is there. So, from the middle you cut 20 millisecond speech signal. So, record a vowel with 16 kilohertz sampling frequency, 16 bit encoding. Then cut 20 millisecond of speech signal. So, let us try for one frame only. Okay, one frame. Then what should the order of the LPC analysis? 16 kilohertz. So, 16K divided by 1000 into plus 2 plus 2, 2 for glottal, 2 for radiation. So, I can say 16 plus 2 is equal to 20. So, I can get P is equal to 20. Then implement AZ in a program and implement 1 by AZ using a program. In MATLAB or C, anywhere you can write the program. Implement AZ and 1 by AZ and calculate Ki value. So, for implementation I require Ki value. So, Ki value can be calculated either using autocorrelation function, from there you can calculate Ki value, or directly you can calculate Ki value. I will show you that slide how to directly Ki can be calculated. Okay. So, if I know calculate the Ki value, then implement AZ and 1 by AZ using a MATLAB program. Try it. If you have any confusion, write my in email, or you can forum, you write it that I cannot implement it. Okay. Then implement AZ. Once you implement AZ, so I implement AZ in a program. What is the input? Input is SM, which is 20 millisecond signal of A. So, if it is 16 kilohertz, so there will be 320 sample value. 320 sample value, SM is nothing but a 320 sample value. So, apply this 320 sample value through AZ and find out the error signal. Now, apply this error signal and implement 1 by AZ, same K value. K value will be same both function, and see whether you get back the SM or not. See whether you get back exact EM, you apply input to the 1 by AZ and see that whether you get back the SM or not. For particular one frame. Now, if I want to synthesize whole A, then the frame will be repeated. Okay. So, that implement and told me in the forum. Report me in the forum, implement it. Okay. So, this is the direct computation of K parameter. What is the K parameter? How do we calculate the K parameter? So, K value actually minimize the error. So, if I say I am not writing in a board, if you see in the slides, K forward. So, E forward prediction error mean square forward prediction error is this one. So, you know that EIM can be written as EI minus 1 m minus Ki into Bi minus 1 m minus 1, that whole square. Now, how do you minimize? I differentiate with respect to Ki and equal to 0. So, check the differentiation and find out the Ki forward value. I can find out the Ki forward value. Once I get the Ki forward value, similarly I can calculate the Ki value for backward error. Then I can say the K is called Parker, partial reflection coefficient or partial correlation coefficient. Okay. So, if I say that partial correlation coefficient in Ki, then it is nothing but root over of Ki forward, Ki forward equal to Ki backward, then either Ki forward or Ki backward you can take. Okay. Or you can use covariance methods, which is equivalent to call I can say the Borg method. So, total error is forward error plus backward error. So, mean square error, forward error square plus backward error square, and then take the differentiation with respect to Ki and make it 0 and find out the value of Ki Borg. Okay. So, you can, if you know Ki, you can implement Az, or if we know EI1m and EI. So, based on the previous error I can find out present Ki, okay or not. So, using this equation you can implement Az or 1 by Az and record a vowel A, take a 20 millisecond window, pass through Az, find out Em, then pass the Em with 1 by Az implementation and get back that Sm again. Okay. So, error signal consists of excitation and gain. If it is noise signal, if it is fricative sound, then it is nothing but a gain and noise. Okay. So, this is the summary. Now, comparison, you may compare the different methods, what are the different methods for LP extraction. If you see that lattice methods only use combine the two stage covariance, that correlation or autocorrelation or correlation matrix and linear solution. They have combined both together and use single stage. So, those are the computational issue is there, you can read it from that slides. Stability issue is there, generate for autocorrelation, the guaranteed for autocorrelation and guaranteed for lattice method, but covariance method it is not guaranteed, because if it is a large matrix, then you know the upper triangular matrix, lower triangular matrix. So, there has some problem. So, you can say the covariance method is not guaranteed, but autocorrelation method and lattice method guaranteed, stability is guaranteed. A choice of LPC analysis already I have discussed, Fs by 1000 or Fs by 2, 3 to Fs by 1000 plus 2 for Gödel excitation and 2 for the radiation. Okay. Estimation of for. So, if I know Az, I have already discussed that if I know alpha 1, alpha 2, alpha 3 and all LPC coefficient alpha 4, those represent the transfer function at that position, and each pole, or if it is those are representing the pole position, equivalence to the pole. So, each pole represents the formant frequency. So, actually alpha 1, alpha 2, alpha 3 should represent the formant frequency is the frequency plane. Now, if I take 14th order, then the alpha value which is not close to unit circle not give you the formant frequency. So, the alpha value which root value which is close to the unit circle give you the formant frequency. Then I have already said in my tube class, this LP analysis is related to the lossless tube model. If you remember that this is the lossless tube model, if I consider all tube has same dimension, then I know L equal to n into del x. So, you know that Rk, value of Rk is nothing but a k plus 1 minus reflection coefficient, a k plus 1 plus AK. Okay. So, if I consider Rg is equal to 1, then Rn equal to RL. Rg is equal to 1, then Rn is equal to RL, and Rn equal to RL equal to rho C by An divided by ZL. So, let ZL is equal to 1 also 1, forget about that. So, this is the reflection coefficient. Now, I give you the problem. The problem is here. Can I estimate this area function from the speech signal? I want to estimate that, suppose I produce I want to how the area function is changing during the production of So, how this area function is changing? Let us this tube is model. So, if it is a pth order LPC analysis, so I can say the tube is divided into p number of section. So, if you relate that ki value and rk value has a relationship, or ri value has a relationship. So, minus 1 minus ki is equal to ri. So, you know that the rk value is minus 1 rk plus 1. So, rk is nothing but a minus ki, or you can say ri, let us see this, ri is equal to minus ki. Okay. Now, if I know rk value or ri value, then I can express ak plus 1 in term of ak, or I can say that ak plus 1 divided by ak is equal to 1 minus, it will become 1 minus ki divided by 1 plus ki, if I put the ki value. So, if I know the ri value, if I know the ki value, I know ri value. Once I know ri value, I can find out the ak plus 1 divided by ak. So, if I know the previous tube cross sectional area, then I can find out the what should be the cross sectional area of the next tube. So, if I say beginning tube, let us A1 is equal to 1, then I can estimate A2 if I know A1, K1. So, if I say A1 is equal to 1, then I can find out A2 if I know K1, 1 minus K1 divided by 1 plus K1. Then if I know K2 and A2, I can estimate A3. So, that way I can say, if I know first cross sectional area is 1, then I can say how the cross sectional area is, different cross sectional area is created during the production of that vowel, from where I estimated that ki value. Okay. So, for a given vowel, I can draw the, this is given taken from the Professor Raviner books, that if this is my vowel signal, those are the area function. So, area function I can draw if I know the speech signal. Okay. So, reversely, if I know the area function, I can generate the speech signal, that is a tube synthesis. Now, if I know the speech, I can find out the what kind of constriction or what kind of different cross sectional area is made during the production of that sound. Okay? Thank you.